In this video, we're going to look at some of the other properties of these intermolecular forces, such as surface tension, viscosity, and capillary action. Now, surface tension is a property of all liquids, and basically the liquids at the surface don't want to be at the surface because they have nothing to interact with. They're just interacting with air. They're losing out on these intermolecular forces. And so, in general, what liquids will do is that they'll form perfect spheres. A sphere will minimize the amount of surface tension there is, as long as there's no gravity. We know on Earth, like water forms droplets because there's gravity pushing it down. If there was no gravity, water would be a perfect sphere, right? And the layer of liquid or water on the surface behaves much differently than water on the interior, not at the surface, because the surface molecules want to be in the interior, so they have a net pull, and there's a cohesive forces acting there, right? So on the surface, it's kind of like a skin because the surface is resisting making more surface, because if you make more surface, more water is interacting with air, which it doesn't want. So you get this thing called surface tension that allows you to float a paperclip or have bugs walk over water because it is resisting breaking to make more surface water. Right? So let's break this down again. So molecules on the surface, they have fewer neighbors around them because they're interacting with air. So they're really less stable than those in the interior. And in science or in chemistry, when we say something is less stable, it has more potential energy, right? And when we talk about surface tension, that is the amount of energy you need to put in to increase the amount of surface area. That is, to increase the amount of liquid interacting with that gas. And it has to do with intermolecular forces. So water has a higher surface tension than benzene because water has these hydrogen bonds, right? So interior waters can hydrogen bond up to 6 groups, while surface molecules will only hydrogen bond with, let's say, 4 groups. Right? So what type of factors affect surface tension? Like I said, intermolecular forces. The stronger your forces are, your intermolecular forces, the higher your surface tension will be. That is, the more energy you need to put in to create more surface. Also, if you increase the temperature of your liquid, you will increase the kinetic energy of your molecules. And that will make it easier to stretch the surface because the molecules will have more energy, so surface tension will actually go down then. The next property we're going to look at is viscosity. And viscosity is the resistance to flow, or how syrupy your liquid is. And the unit for this is the pose, and P. And 1 centipose is the viscosity of water. But basically, the more intermolecular forces you have, the higher viscosity. So let's look at our hydrocarbons, where pentane, hexane, heptane, octane, nonane. All we're doing is adding 1 carbon each time. When we do that, we're stretching out our molecule, giving it more surface area, which means we have greater intermolecular forces, which means we have higher viscosity. So the higher the intermolecular forces, the higher the viscosity. All right. So what factors affect viscosity? We already talked about 1, stronger intermolecular forces. Also shape. The more spherical it is, the lower the viscosity. 1, if you're spherical, you're going to have low intermolecular forces to begin with, but also you'll be able to roll more easily if you're a sphere. Also, temperature. The higher the temperature you are, the lower your intermolecular forces will be, and the lower your viscosity. You raise temperature, you're also raising your kinetic energy. Remember, kinetic energy is movement energy. Right? So if we look at water, you can see viscosity changes quite a lot as you increase temperature. So those are the three factors you want to know that affect viscosity. The last property we're going to look at is capillary action. That is the ability for a liquid to flow up a tube against gravity, and the narrower the tube, the higher the liquid rises. So capillary action, you want to think of a classic thermometer, right? That's what's happening. The liquid is climbing up the glass tube. And capillary action, there's two forces we have to think about. One is cohesive forces, or that is the forces that are holding the liquid together. The second is adhesive forces, that is liquid being attracted to the tube itself, right? So what's happening is when we put a liquid in a tube, the liquid is attracted to the side of the tube, and so it will bind to the tube and start to climb up it. Well, the liquid is also attached to itself, it's attracted to itself, so when liquid climbs up the side of the tube, adhesive, it also has cohesive forces that are holding the liquid together, bringing it up with it. And the narrower your tube, the further up you can climb against gravity. And you're going to stop climbing once gravity is equal to your adhesive and your cohesive forces. And through this capillary action, we get the phenomenon of the meniscus. And you've seen this working in the chemistry lab, where if you look at water inside of a tube, you see it looks like a U. That is because you have your cohesive and your adhesive forces competing. So water is concave because water is more attracted to the glass than it is to itself. So your adhesive is stronger than your cohesive. So you'll have more water climbing up the side than you'll have coming with the water. While mercury is the opposite. The cohesive forces in mercury, which is a metal, are stronger than the adhesive forces than the glass. So mercury wants to be with itself more than the glass, and what you see is a convex shape where the mercury looks like it's bubbling out. Right? And that's it for this video, and I will catch you in the next video.